Good morning. My name is Philip Warrick. I'm going to be presenting this talk by Mahdi Shamsi, our postdoctoral researcher, who was hoping to be here as late as the beginning of the week, but visa problems prevented him from coming. I think we may have him on a Teams link for him to actually listen and perhaps respond to a question if he got on. I'm not sure if he got on or not, but hopefully he did. So this is a talk about continuing our deep learning approach to HIE risk detection and implementing a latent representation approach to this. So as you've heard before, the objective is to detect the risk of HIE developing, because detecting HIE, of course, is a bit too late. We want to incorporate all these precursors into the system to give us an indication that HIE is a risk, and we're focusing on the uterine pressure and the fetal heart rate for this. In this case, we're applying a deep learning model to learn in a pre-training phase good learning representations of the FHR. And we do that with a variational recurrent neural network called VRNN, which is a variational encoder adapted to time series. So when we do this first phase, we're simply trying to extract good features, and then as a second phase, then we hope to use these features for our real-world problem, which in this case is deciding this risk of developing HIE, but it could be other things as well. So why are we using this particular network? Well, we have a really unbalanced data set, of course, with lots of healthy cases and very, very few HIE cases. And the idea is to try and take advantage of this majority class with a robust pre-training that can include a lot of these cases. And VRNN and VAE, variational autoencoders in general, can deal with a high dimensionality of the data. And what does that mean in our context? What does high dimensionality mean? Well, first of all, we have long recordings, potentially, hours and hours of FHR recordings, but also of varying lengths. And recurrent neural networks are very nice for variable length recordings. But secondly, in terms of the content, the information content at each time step, we have kind of these broad bands that have been identified and defined very rigidly, actually, by the clinical guidelines. For example, the XL-D cell band in the middle there are defined as by their duration, 15 seconds, for example, minimal, and 15 beats per minute, minimal amplitude. But this is, in reality, physiology does not respect these guidelines, and it is a spectrum. So we have all of these things, baseline, XL, and variability, happening at the same time. So the components are superimposed, and that gives you a sense of what a high dimensionality might mean in addition to the time. So we want to characterize the essential characteristics in a latent representation. That's the goal. And we want to do it for our time series. So that's why we're choosing a long short-term memory backbone for this. And thirdly, we want a probabilistic approach and a generative approach because we want to understand how the data might be generated. If you can understand where FHR comes from, in a sense, where its sources are, you might have achieved some understanding of that signal. This is an overall block diagram of the VRNN-based model, which we call sequential VAE. And it starts at the front end with this transform that we've talked about before, taking the 1D, one-dimensional FHR signal and transforming it into by the scattering transform into a spectral description of the signal. And given that scattering transform representation, we feed it into this basic part of the block part of the system, which is the autoencoder part, where you have an encoder, a decoder. Those are the basic autoencoder building blocks. But in addition, we have this recurrency from the decoder back to the encoder with an RNN, which allows us to incorporate time series correlations between the time steps, which does not come with the vanilla VAE. So once again, scattering transform, it's an encoder and a decoder that are learned in tandem so that you get both a good reconstruction of the signal at the decoder, but importantly, you get a good latent representation of the FHR, which we can use for the downstream task that I mentioned earlier. In this case, we have a classification head or a classification network that we can subsequently train based on the pre-training for the VRNN. So more specifically, for the pre-training, we started with 1,500 healthy cases. These were healthy babies that had verified with blood gas results that they had no acidosis. And from these recordings, we extracted almost 30,000 10-minute epochs, so approximately just over 3 hours per recording, drawn from the last 6 hours of before delivery. Again, on the top, we have the raw FHR, and below that is the representation by the scattering transform, starting from the high frequencies at the top near the 0 level down to the lower frequencies at the bottom at level 11. So here's an example of that same scattering transform representation of the FHR with its 11 dimensions. Put through the VAE, we have a latent dimension representation. This shows 7 dimensions vertically by, I believe it's 150 time steps. You see those blocky things. We have it's kind of an image representation of 10 minutes in this latent dimension. It's not really interpretable, but we're hoping that it's preserving the information. After that, after reconstruction, you see that we're back to where we started successfully. The reason that we go through this is to ensure that our VAE doesn't fall into this collapsed mode where it simply propagates the input over to the output, and then you obviously get good reconstruction without doing much interesting network building. Just as an example, here is what the scattering transform looks like when we have no training, It's basically random. And after training, we go from this random place to the trained reconstruction, and you see that the errors measured by mean squared error drop drastically to close to zero. This big red spice is kind of misleading. It's the untrained model not doing very well, but just focus on that big spike at zero, meaning that we've reconstructed well. Here's some preliminary results using the latent representation. We freeze that model and feed it into our very basic classifier that's also LSTM based. And we trained on the last 6 hours and tested on the last 12 hours. And here's 5 folds out of the 10, I guess, we're just to not have such a busy plot. It basically is starting around a random classifier at the beginning and moving gently upwards over time. We're still, this is very hot off the press results. Of course, we have to not show AUROC eventually, but choose a threshold and show our sensitivity and specificity. Just as a sanity check, we wanted to see if the latent space actually preserved anything meaningful, because looking at the image that I showed you before, it was hard to interpret. But if we tried to correlate those latent dimensions to, say, XL, decel, baseline features like height and area for the XLs, decels, and duration for the baselines, looking at some really basic statistics of the latent dimension, min, max, mean, and standard deviation, do we see any correlation? And indeed we do. The hot spots for, say, here's 2 latent coefficients out of the I believe it's 7 total latent dimensions. Looking at 2 of them, we see that the acceleration average height was captured best by the minimum value of latent coefficient 3, and at the same time, the deceleration average height was captured best by latent coefficient 6, the maximum value. So this was just a quick check to see, not that we've done anything special, because there should be correlation from our scattering transform or even the raw signal itself, of course, to these, if these relationships do exist. But we wanted to make sure that we had avoided this collapse phenomena that I mentioned earlier. So here's the nice values. And in conclusion, we've shown that we can create a latent representation using an LSTM sequential model, and demonstrated some preliminary classification results using that model, using the latent representations, and confirmed that these actually do correspond to meaningful FHR characteristics. So we'd like to, in the future, instead of freezing the VRNN as we are now and training the classifier in isolation, we'd like to train them together. And secondly, we'd like to introduce the uterine pressure into the equation because it has some strong correlation to the decels, of course. And finally, go further in what I've shown you most in the last few slides to decide or to determine which of these latent patterns might be most discriminating. And this is the slide that you've seen before, I think. Thank you very much.